Hello, hello, am I audible? And is the screen visible to you? Hello, am I audible? And is the screen visible to you? Hello,
Yes, yes,
okay, and is the screen visible to you?
yes.
Okay, uh, okay, thank you, Mr. So, okay, so before starting, let me know, do you have any question or any doubts from previous sessions or any doubts from the live sessions or anything else? If you have any doubt, please ask. If you have any question, please let me know.
Excuse me, sir.
Hmm,
Why
yes.
state of rationals not locally compact?
Well, one. Let me check everything what to find. Okay. Yeah, so your question is why Q is local comp. Q is not local comp, right? Okay, well, so okay, so 1 minute. So question is why the Q is not locally compact. That is the question. Okay. So firstly, what is the definition of locally compact? Suppose X base space and suppose X belongs to X. Then capital X is said to be. So I mean, so of course, first let's recall the definition of local compact. Okay. So for all, I mean, so X is said to be locally compact at X if any compact subspace of little x contains an open neighborhood of x. So this is what we mean by locally compact. That is, if we take any point and if we take any compact subspace around that point, we will get an open neighborhood around that point inside the compact. So that is what I mean by locally compact. So locally compact. Okay. So now suppose let Q be locally compact. Okay. So so and suppose X belongs to Q. So this means what? X belongs to open AB intersection Q subset of K subset of Q. What is K? K is a compact subspace of Q. Correct. So this means what? So well, so now K is a compact subspace of Q. Okay. Now X belongs to open AB intersection Q. Okay. So by density, what we can do, we can choose uh, um uh, Rn, the set of irrationals in AB, such that Rn goes to X. Correct. We can do this like that. And this implies what? This implies that Q intersection, I mean the capital K intersection Q complement is also non-empty. But that is not possible, so there is a contradiction. So Q is not locally compact. Okay. Do you understand?
Yes, yes.
Okay. Do you have any more questions?
No, no, this time.
Okay. Well, wait for 2 minutes. I shall be back after 2 or 3 minutes. Well, sorry for the inconvenience. Actually, well, so okay. So Mustaq, do you have any more questions?
No, no.
Okay, thank you. Okay, so Mustaq, so today we shall go start with some exercises regarding normalness and regularity. Okay. So, so let's see how much we can go by today itself. If you have any questions within the solving, please stop me and ask questions. Okay. So yeah. Okay. Well, so let's solve the questions itself. So first question. So first question is show that if x is regular, then every pair of points of x have neighborhoods whose closures, sorry, whose closures are destroyed. So what does excess tell? It tells that it is asking to show that suppose f is a regular space, then every pair of point of x have neighborhoods whose closures are disjoint. Okay, so this will be solved by only using the definition of what definition of course definition of regularity. Uh, but try to first solve yourself. I shall wait for 2-3 minutes. Then I will solve it for you. Okay. You need to use the criteria of regularity. Okay, so there is a definition. Of course, we have seen there is a different there is a criteria of regularity also. You need to use the criteria in order to solve this theorem. Try to solve it. I shall wait for 2-3 minutes. In the meantime, let me see what the problems that we can do by today itself. Please try to solve it. Okay. So let's see how to solve it. Okay. So let A and B belongs to X, and suppose A not equal to B. That we are choosing A and B to be distinct. Okay. Now the since X is regular, so it is Hausdorff, of course. Okay. So there exists disjoint open sets A and B with A belongs to A and B belongs to B, of course. Then by criterion of regularity, what will you get? We'll get U and V. Of course, these are open. Such that A belongs to U subset of U closure subset of A, and B belongs to B subset of B closure subset of B. And with U intersection V, of course, empty. So these implies this U closure intersection of V closure is also disjoint. So this is what we need to do, right? So what the statement is that what that every pair of point of X have a neighborhood closures are disjoint. So here in this solution, this final U and V are those neighborhoods of A and B whose closure also disjoint. Okay. So this is the thing. I shall wait for throughout 3 minutes. Please go through the argument, try to understand, and let me know. Do you have any question or any confusion? Okay.
Hello, sir.
Yeah. Just tell me.
Can you explain why, for a countable dense space, every collection of disjoint open set in X is countable?
Okay. So I'm sorry. Could you please repeat the question? Okay. Could you please repeat the question?
Why, for a countable dense
Okay.
space, every collection,
Okay. Okay. I understand the question. So the question is that for every counter, there's also every collection of disjoint open sets is countable, right?
yes, yes,
Yeah, yeah. Oh well. Okay. So the question is as follows. Let capital X be a countable. Sorry. Let capital X has a countable dense subset so that every collection of disjoint open sets in X is countable. Okay, so this is what it is. So how? So let capital D be let capital D be a countable dense subset. So basically, first of all, let me tell you clearly that this solution does not involve any complicated thing. You need to only use the denseness or its equivalent property, the equivalent criteria labeled. That's all. Okay. So let capital D be a countable dense subset of X, and let C be a collection of open subsets of X. Now, since the D is dense, this implies what? Intersection D non-empty for all open set U in X. Okay. This implies what? This implies U naught belongs to U intersection D for some U naught. Okay. Now this collection C is disjoint. So this implies what? If C is uncountable, then D will become uncountable also. And that is a contradiction. Okay. So what? So C will be countable only. Okay. So that is the thing. Do you understand, Mustaq? So basically, the solution does not involve anything complicated. So here you need to use the what? Use the equivalent criteria denseness,
Yes, yes.
namely dense implies it will intersect any open set. So then you need to use a disjoint case. That's all. Okay. It has really nothing complicated. So, do you have any more questions? Mustaf, do you have any more questions? Okay. So let's get back. Okay, so let's get back to original business. Well, so the okay. So the second question that from our exercise is the following, namely, show that if capital X is normal, then every pair of disjoint closed sets having neighborhoods whose closure are disjoint. So the statement goes as follows: suppose X a normal space, every pair of disjoint closed. So if X is a normal, every pair of disjoint closed subspace having neighborhoods close a disjoint. So the first problem was regarding regular. The second problem is almost same, but regular represents normal. Now try to put the criteria for the space being normal. Don't use definite. Use the criteria of the space as normal. Use criterion. Use criteria of normality and try to solve. Okay, think about it. Take your time and try to solve it by yourself. Well, so I will. So how to solve this? So this problem can be solved as previous problems. So let same argument. So let A and B be disjoint, closed subsets of X. Now since capital X normal, so there exists disjoint opens U naught U1 such that A subset of U naught and B subset of U1. Okay, then by criterion of normality, there exist open sets V0, V1 subset such that A subset of V0, subset of V0 closure, subset of U0, and B subset of V1, subset of V1 closure, subset of U1, with of course V0 intersection V1 and B. This thing tells that V0 closure intersection V1 closure at B. And this is what we need, right? We need to get some neighborhood with empty with disjoint closure, and this is what we are getting, correct? So that is the argument. So this is it. Okay. Oh well, sorry. Well, so this is clear to everybody. So now let's move to the next question. So the next question is that, yeah, okay. Let capital X and capital X dot denote a single set under two topologies, tau and tau dash respectively, and assume tau dash subset of tau. Now question is, if one is Hausdorff, then what about others? So this is the question, okay. Think about it for a minute. I shall get back after few seconds. well. So, one, uh, huh. So now question is, if one of them is house drop, then what about others? Suppose. So the what is the given condition is tau prime is subset of tau. Correct. So so tau subset of tau prime, correct? And suppose let x tau prime is house drop. That is the in this equation the right side is house drop. Okay. Claim is then x tau will be house drop. How to do it? So let x y. Uh, okay, so it's a mistake. So our claim should be something. So let x tau. So let the small is house drop. Then we need to take a bigger. So let x y belongs to x with not equal. Okay. So this implies what? There exists disjoint open set U V in where in x tau such that x belongs to U, y belongs to V. But tau such that tau prime, this implies what? This implies U V also open in x tau. That's okay. So this implies what? We are getting open sets in x tau dash and x and y points with x belongs to U, y belongs to V, and empty. Okay, so that is so there's no what. So this tells that smaller is house drop. So if tau subset tau dash and left side smaller house drop, then big one will be house drop. Okay. So this is the thing. So of course now the question is what about converse? So think about it. No, I mean the point is that so big little one is house drop implies big one. So we need to show big one house drop, not the little house. So what? So we can choose tau dash to be R with indiscrete topology, and tau to be R with discrete topology. So clearly tau dash contains tau dash house dot, but tau is not house dot. So this argument, okay, there is really nothing to it. Okay. Think about it and let me know. Do you have any question, doubt, or else we shall go for the next question. Okay. So so uh, so let's put the next question. So next question is, let f g x to y be continuous. Assume y has show that all those x are at fx equally the explosion x. So now try to use the some properties of Kraut-Haus roughness and try to solve this problem. I shall be back after 2-3 minutes. Yeah, okay. So, so, so Mustaq, are you able to solve this question? Or any idea at least how to start this problem? No need to hesitate. You can, whatever the arguments come in your mind, you can, without hesitation, you can share the argument. Okay? Okay. So, let's see how to solve this problem. Okay. So one minute. Okay. So, so observe that what is given. The given y is house group. Okay. So y house drop it is equivalent to saying that diagonal of y. This implies y belongs to y cross y. This is closed in y cross y. Correct. Now define what? Define h from x to y cross y by x going to fx comma gx. Okay. Now h is continuous since f and g. Okay. Now since this thing is closed, so h inverse of diagonal of y should be closed in x. Now H inverse diagonal Y, this thing what? This thing contains all those x's that HX belongs to diagonal of Y. This means what? This contains all those x's that Fx equal to Gx. So this implies what? So this tells what? So this tells that all those x belongs to x at Fx equal to Gx is this thing is closed in X. So this is the argument. So look, so basically the trick is nothing but hmm. So the trick is basically nothing but since the y is given a house drop, so there is a delta is a closing y cross. So we can define h two boundaries closed, and we can take the inverse image of the close. That's the whole problem. Okay, so there is really nothing complicated here. So let's go to the next question. So Mustaq, tell me, do you have any question or any doubt? Mustaq? sir, tell me, do you have any question or any doubt? Okay. So let's move to the next question. The next question is the following. Well, just let me mention that the question, the solving of this question is not trick unless and until you do practice by yourself. Okay, realistically, these are not complicated at all. You need to practice a lot in order to solve these problems. Okay, so the question is the following. Let P x to y be a closed continuous such show that if x is normal, then show its y. So the question is that suppose P is a map from x to a continuous surjective, show that if the domain is normal, then codomain is also normal. Think about it and try to solve by yourself. If not, then I shall solve it for you. Oh well. So yeah, it is quite tricky, I must say. So this problem can be solved the following way. Yeah, just observe this. Let's look at solution. It is actually a little tricky problem. It is not, the solutions are not direct. Okay. Observe P inverse W uh, subset of U. This is same thing as saying that Px belongs to W implies X belongs to U. This is same thing as saying that X does not belong to U implies Px does not belong to W. The same thing saying that P of X minus U subset of Y minus W. The same thing as saying that P of X minus U intersection W is empty. So this implies what? This implies if P inverse Y subset of U, where U is an open in X, then P inverse W subset of U for some uh, well, so let me so now choose Y with P inverse subset of U, where U is the open subset of X. So this implies Y does not belong to P of X minus U, and X minus U is a closed subset of X. So this implies there exists a neighborhood W constant Y of little y with W intersection P of X minus U empty. So this implies what? This is equivalent saying that P inverse W subset of U. Correct. So first tell me that till now these things are fine or not.
Yes.
Okay. So this is one thing. Now secondly, suppose B was subset of Y and suppose let P inverse be subset of U for some subspace B of Y and some open subspace B of X. Then P inverse W subset of U for some neighborhood W of Y of B. How to do it? So for that, so for each Y belongs to B has a neighborhood WY such that P inverse WY subset of U. Then W is equal to union WY is then a neighborhood of B with P inverse W subset of U. So so this is the two things first we want to prove. Now let's so what we have proved till now, we have proved two things. So we have proved two things. Namely, the first one is that so basically we have proved two things. First one, those statements are precisely as follows. If P inverse Y subset of U where U is an open subset of X, then P inverse W subset of U for some neighborhood W subset of Y, or for this is one thing. And second thing is that if P inverse B subset of U for some subspace B of Y and some open subspace E of X, then P inverse W subset of U for some neighborhood W of Y B. Okay, so these are two things that we have proved till now. Okay, now let's prove the main thing. Wait for a minute. Wait a minute. Well, so okay. So now let's get back. Now let's try to prove the original question. Wait a minute. Okay. So so now so now since the points are closed in X, because being normal, X being normal, and P closed, so all points in Px are closed. Okay. So this tells what? This tells the fibers through a subset of X are closed. Now let y1, y2 be two distinct points in Y. Now since X is normal, so we can separate the disjoint closed sets P inverse y1 and P inverse y2 by disjoint neighborhoods E1 and now using now using basically the previous those criteria lemmas. Now choose neighborhoods W1 and W2 of Y1 and Y2 respectively, such that P inverse W1 subset of U1 and P inverse W2 subset of U2. That is, here we are using this second result proved at the starting. Okay, this is the result that we are used, and of course then W intersection W disjoint, and this implies Y Hausdorff. Okay, so this tells that first Y is Hausdorff. Now the essentially the same argument tells we can separate disjoint closed sets in Y by disjoint open sets. So Y is normal. Okay. So this is the argument. So think about it. Let me know. Do you have any question or doubt?
Hello, sir.
Yeah, tell me. Okay.
Why R with lower limit topology is not matriceable?
Well, I shall explain. Before that, let me know. Do you understand this argument properly or not?
Yes, I understand the previous one.
Sorry. Well, okay. Hmm. Okay. So your question is that why are with lower limit topology is not matriceable? Why are with lower limit topology not matriceable? So suppose R with lower limit topology is matriceable. Okay. Now R with lower limit topology is separable, but being matriceable, it becomes second countable. Why? And then Rn will be one matrix. So R becomes second. So okay. So if R is metrizable, so that will imply that R will lower limit is separable. And being metrizable, a separable metric space will be of course second countable. But in just why? Because last session we have done an exercise that metrizable space, if it is say either separable or linear, then it will be second countable. So that was exercise previously. Anyway, but this implies what? This implies, sorry, but we have seen this is not possible. But we have seen that R with lower limit topology not second countable. Already seen in previous sessions. Okay, so that is okay. Hmm. Well, so yeah, so that is the argument. So Mustaf, do you understand the argument? Well, so I have this clear to Mustaf. Okay, so okay, so now uh, uh, okay, well, so the next question as follows: show that closed subspace of a normal space is normal. Okay, look, try to solve this problem. Both sides so normal. How to do it? So, of course, one thing is we need to go along the definitions. So, let capital X be a normal space and capital A subset of X to be a closed subspace. Okay. Now we need to show what? We need to show capital A is also normal. Okay. So it can be proved by using the definition, but let's use a trick here. So what we can do? So solution. Let if1, if2 be two closed subspace. Okay. Then if1, if2 will also be closed in capital X. Okay. Then by Uritian's lemma, there exists a continuous function map f from x to 0, 1 such that f of f1 is equal to singleton 0 and f of f2 is equal to singleton 1. Now we have some map A include capital X to 0, 1. I it is F. Then what? F compose I whole inverse singleton 0 is equal to F1 and F compose I whole inverse singleton 1 F2. Now this implies what? F compose I whole inverse close 0 open half. This contains F1 and F compose I whole inverse open half close 1. This contains F2 and these two things, this and this, are what? Are open in capital A. So this is what? If1 of course and of course and of course what? We are disjoint. Okay. So this is implement. So this tells that capital A is also normal. So Uritian's lemma can be used in order to show that some space is normal. Okay. So that is the thing. So think about it. Let me know. Do you have any question or doubt regarding this, or else we shall go for the next question.
No, sir.
Yeah, tell me.
Why RK is not house dog?
Well, that's a good question. One minute. Well, so okay. What does to us? RK is house drop or RK is not house drop? What just you asked?
Why RK is not house dog?
Okay. Okay. So possibly this possibly there is a typo in the question. RK is actually house drop. RK is house drop. Why? Because R with usual topology, subset of RK and R with usual topology is what is of course house drop. So RK is also house drop. Sorry. So RK is also house drop. So what from where you are the you are putting you are asking the question there must be separating this RK is a house drop space. Okay, that is the thing. Okay. Hmm. Okay. So now, do you understand, Mustaq, my point that why RK is house drop? I mean, RK is not house drop. It's not possible because RK is already house drop. Okay. So now let's go for the next question. So the question is well. So we have already so well we have already seen the so there is something known as Wilson's lemma in case of topological space. So of course in metric space the same is also true. Well, mm, but in case of metric space there is an easy way to Wilson's lemma. So basically, so let capital X be a metric space. This is a question, and let A and B be two closed subspace of A and B. Construct a function f from x to 0, 1 such that f of 0 is equal to A and f of 1 is equal to B. Sorry, that it does not make sense. Construct function such that f of A is equal to singleton 0 and f of B is equal to equal to 1. So try to construct a function. Okay, we of course need to use the metric itself. Try to construct, think about it, let me know. I shall wait for 2-3 minutes. Oh, well, so easy function is as follows. So define, f fx is equal to dax divided by dax plus dx. So of course, so obviously, first of all, 0 less than equal to fx less than equal to 1 for all x, okay? And for a belongs to a, f of a is always 0. And for b belongs to b, f of b is equal to d a comma b by d a comma b plus 0, which is always 1. Okay. So this thing is our desired function. Okay. So these are them. So our matrix space construction of this type of functions, so which of them is quite easy. Oh, well, now let's try to solve some more problems. So wait a minute. Oh well. So now, so now the question is the following. One. So let me check everything is fine. Okay. Okay. So the question is as follows. Uh, oh well. Okay. So the question is as follows. So question is, let capital A be closed subspace of X. Show that if X is Lindelof, then A is also length. This is what need to do. So 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 capital X the close out space, and given the space, bigger space, the length of initial X is length of. Think about it. Use try to use the definitions and let me know. I will wait for 2 3 minutes. Well, so how to solve it? So let so linear means what? Linear we want to show every open cover as a countable subcover, correct? So so how to choose the countable subcover? So I mean so let U alpha be an open cover. Okay. Let U alpha be an open cover. That is a subset of union of U alpha. Okay. Now x is equal to x minus a union of U alpha, and x minus a is also open. So x minus a union this collection U alpha is an open curve for x. Okay. So this implies that x is x minus a union countable collection of UIs. It's possible countable. So this implies a subset of union of U alpha I is 150. So that is A is covered by countable, that is the countable sub collection of UIs. This is the countable sub collection of UIs. and this tells that A is length allowed. So these are going. So think about it. Let me do the So basically, what we have done, basically we have done nothing new. We simply use the closeness of the given space and try to show that using the Lindelof index of the given bigger space, try to show that the small space will have a countable subcore of any open cover. Okay. Well, so let's go to the next question. Okay. Hmm. So now, so next question. So next question is as follows. Show that please. Lindelof. Sorry. Show that if capital X is a countable product of spaces having countable tens, that is then X has a countable dense subset. So given a space is a product countable, then we will show that the count given is a counted product spaces having countable dense subset, we need to show that capital X has a countable dense subset. How to show? I mean, it is obviously easy, but if there's been no other argument, or else I shall write down the argument. Well, wait, I shall get back to the opportunities. Well, how to solve it? Solution. So let capital X is a counter product of spaces where xi is separable. Okay. Let dI subset of xi be a countable dense subsets. Okay. Now this implies what? This implies that product of I is equal to 1 to infinity, is also countable, and product of di is equal to 1 to infinity di its closure is equal to, of course, in product topology di closure is equal to I is equal to infinity xi is equal to x. So this implies what? This implies product of di I is equal to 1 to infinity is dense subset of capital X. Okay, so these are what. Oh, well, so these are what. Now, now there is one interesting question. Uh, well, wait a minute. Yeah, okay. So there is one question which we have, sorry, which we have seen in the previous session, and the question is as follows. And I feel that I should rediscuss that purpose again. So let capital X be a Hausdorff space and A be a it also be its retract. Show that A must be closed in X. How to solve it? So by the way, what is the definition of retract? Retract means there exists a continuous map R from X to A such that R restricted space is equal to identity of. So this is what by unit. Now try to show that if a space is retract in Hausdorff space, then that must be closed. well, so we want to prove that it's closed. So closed means what it is going to show that x minus a is also open, correct? So let x belongs to x minus. This implies what? This implies x does not belong to, okay? And this implies what? This implies at least Rx not equal to x. This implies there exists open set U, V, U containing Rx, V containing X such that U V open and U intersection V empty. Correct. Now, no, wait. No. Okay. Now, this will imply that X belongs to R inverse U intersection V. Correct. Now, claim is that R inverse U intersection V, this intersection capital A is empty. So, but if suppose T belongs to R inverse U intersection V intersection capital, this is what? T belongs to U, T belongs to V, and T belongs to A. T belongs to A, and this thing together implies RT is equal to T. So this implies what? T belongs to U intersection V. It's a contract. This implies U intersection V empty. But here we have U intersection. So this gives a contradiction. Okay. So this tells that, and of course R inverse U intersection V is an open capital X. So this tells what? So this tells that R inverse U intersection V subset of X minus. This implies what? And continue. This implies what? X minus A open. This implies A is closed. So these are okay. So that okay. So that's all for today. Uh, and so that's all for today. So and this is the exercise that we have solved by today itself. So if you have any question in your, you can ask today, or you can also drop an email. I shall get back to you by the next session, or you shall ask your question in the next session. Okay. So yeah. Okay. So let's end here. We shall meet in the next live session in upcoming Friday. Thank you.
Thank you.